watching right now is about Schottky barrier and Schottky diodes. The Schottky diode is named after a German physicist named Walter H. Schottky. The p-type semiconductor is replaced by the metals such as aluminum and platinum. So the junction is formed between the metal and the semiconductor, which also known as metal semiconductor junction or MS junction. This junction creates a barrier which is also known as Schottky barrier. The Schottky barrier is a potential energy barrier where the electrons have to overcome this potential energy barrier to cross the diode.
Next, I am going to tell you about the metal and semiconductor contact reverse bias. Okay, as you can see from the graph, there will be two parts of the graph. Actually, for the right side will be representing semiconductor, while the left side will be representing the metal. So this is the condition when the metal and semiconductor contact is in reverse bias. As you can see from the simple circuit below the graph, the positive probe, the positive polarity is connected to the semiconductor, while the negative polarity of the voltage source is connected to the metal. During reverse bias, the barrier in the semiconductor increases and semiconductor becomes positive because the metal does not sustain a voltage drop. Thus, the electrons in the semiconductor are unable to pass over the barrier from semiconductor to metal. This bias makes the electric field become stronger and increase the degree of bending of the bands.
Metal and semiconductor contact forward bias.
This is the graph for metal and semiconductor contact forward bias. When voltage applied, bending of the conduction and valence bands in the semiconductor at the junction change. The electric field in the semiconductor change at the junction with metal. During forward bias, the barrier in the semiconductor reduces and metal becomes positive. Thus, the electrons in the semiconductor are able to pass over the barrier from semiconductor to metal. This bias reduces the electric field and the degree of bending of the band.
When work function of metal smaller than semiconductor, the contact is non-ratifying and labeled ohmic. Electron move from metal to semiconductor and Fermi level align because ohmic contact provide no barrier. Electrons in the semiconductor will recombine with carrier holes, leaving negatively charged uncompensated acceptor ions in the semiconductor to form a depletion layer which depends on the doping process. When voltage applied, during forward bias, P semiconductor become positive and the barrier to hole flow from semiconductor to metal is reduced. During reverse bias, metal become positive and the barrier to hole flow from semiconductor to metal is increased. The barrier in the metal interface is unchanged.
So, here is the width of the depletion layer where the applied voltage VA is positive for forward bias and negative for reverse bias. This slide shows two formulas where the top formula is the charge density in the depletion layer and the bottom formula is the capacitance per unit area. The capacitance per unit area formula can be rewritten in the following form.
Assuming a uniform ND throughout the depletion layer, we can plot a graph of 1 over Cj squared versus the applied voltage VA.